In life, man proposes, God disposes. If I'd been told I would be handling a topic like this today, I would have likely argued. But it is what it is, life happens. So in today's class, I will be talking about calculus of variation. It's not going to be a simple stuff, and it's okay. It's ought to be simple. That's why you're watching this video anyways. So what is calculus of variation? So calculus of variation is a field of mathematical analysis that uses variation which are small changes in functions and functionals to find maxima and minima of functionals. You understand? So it's not like somebody's going to ask you what is the definition of calculus of variation is, but you might want to take note of this particular point. A curve that maximizes or minimizes the value of a functional is called an extrema. All right, so a curve that maximizes or minimizes the value of a functional is called an extrema. So you might want to take note of that. So the thing is that there are a lot of writings in this stuff. There are a lot of theoretical underpinnings and what have you. But let's just go straight to an example because I think that's what is probably more important to you. So we have a function like this. We have to optimize this function subject to these constraints. All right. So the thing is that what you have here is what is called a functional. All right. So what you're optimizing is what you are calling the functional. So it might be the optimization might be to minimize or to maximize, but whatever it is. So whatever is inside the integral is your functional. Then it is we are integrating with respect to t. T is time. Then we have the upper bound and the lower bound. It's subject to this. So when we move into a different topic, optimal control theory. So we have something like this. They have um. Okay, let's when we get there, when we get to that bridge, we are going to cross it. So how do we solve this kind of question? So the thing is, first we are going to write out the functional. So it is written as f equals 4 x. There's a dot on it. It's not a mistake. Then plus 12xt minus 5t. So now what this by x means, what it means is actually the derivative of x with respect to something. Alright, so like for example, if you have 5 y equals 5x squared, right? So dy dx equals 10x. So in this case, dy dx equals 10x could be written as by y. Yes, so that's just it. So like it's your derivative of the dependent variable with respect to an independent variable. So here by x, what it means is that differentiating x with respect to t. All right, so that's the meaning. So if you differentiate a second time, for example, divide the x gives me 10, gives me by y. So if I differentiate the second time, okay, I have the squared y, the x squared, that will be equal to 10. So I could also write it as dot y, something like so y with a double dot on it, which is telling that I've differentiated y twice with respect to an independent variable. You understand? So now after doing this, so what we are supposed to get now is we are going to be looking for the f, the t. So it's going to be a slanted d. Remember, we are doing a partial derivative. So sorry, so what have I done? The f, the x rather. So what is the f, the x? You have x here, right? So that is going to give us 12t. So that's not all. Then we also do the f, the x. I don't know what it's called, so I'll just call it x dot, right? Which is this guy. Alright, so when you do that, you have 8x, something like this. Alright, so we don't have this type of x here anymore. So your partial derivative, that's simple, so it shouldn't give us any problem. So from here, we now substitute into the Euler's equation. Okay, substitute, or let me just say substituting into the Euler's equation. So what that says is that the f, the x is equal to d, the t, then the other one, the f, the x dot, the f, that's what it's saying. So the f, the x is 12t. So 12t equals to d, the t, then we have 8x dot. All right. So, but the thing is, you might be you might just want to write DDT, all of this. You might just want to equate it to zero since we are differentiating with respect to t and there is no t here. So it might be, um, is it deceived now? Or you might just turn the whole thing to zero. You understand? Doing your partial derivative, there is no t there. But the thing is that recall that I told you that x is equal to the x, the t on its own. So doing a dt of this guy is as if we are differentiating. We are doing a double differentiation. So your dt, okay, of what is here. So it's more or less. Let me bring 8 out. 8 d dt. Then x on its own is the x dt. Of this bar x is so it's more or less like you're having so 8 is still there. So you're having d squared x, the t squared. So it's as if you are differentiating this guy twice. So what that gives us, since you are doing since it's as if you are differentiating it again, so your final answer is going to be 8 and you have x dot dot. So you are differentiating x again. So that's it. So like you might just want to think, okay, DDT 8x should just give me 0. So I should just equate all of the right hand side of the equation to 0. But like I've explained, it's not like that. It was by x, that which was, from here, that's what I was trying to explain from here. Dy dx is equal to dot y, for example. So, like, it's not, I don't know if this is what really, if this is what this really is. Like, um, I don't know if it has to be with respect to time or just any independent variable, you understand? But I'm just trying to like use this as an illustration for you to understand what is going on here. So if you do a divide the x, you understand? So the answer you're going to get is the same thing as your dot y, so point y. If you do it, say if you differentiate the second time, it's more or less like dy dx is dot x, dy dx is dot y, d squared y, the x squared is dot dot y. So dqy, the x cube is dot y. That kind of a thing. So that's just like a different way of representing your derivatives. You understand? And if you look at this, the right dx here could also be called fx. So this is signifying that you differentiated this guy, once. That's why you have one prime on it. So and this other one is f prime prime x. So like different kind of notations. You have this, 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 something like that. But in this particular case, this is what we are using. All right. So now you have 8x, dots there, and after that, dots means the x, the t. So d dt, so it's like two times, right? So that's how we got d squared x, the t squared, and that means 8 is 3 here, so 8 is standing. Then the squared x, the t squared of this that differentiates this guy again. So you get this. Now 12t, substituting that into the equation, you have 8x dot dot. Alright, but the thing that we are looking for is x. So what we are optimizing, we need to get x out. So if you're following, x dot dot simply means I've differentiated x two times. You understand? So for me to be able to get x back, I have to integrate x dot dot two times. So that's just the reverse of differentiation. When you differentiate once, to get what the original function that you differentiated, you have to integrate what your solution was for the first step. So here we'll be having integral 12t dt equals to integral 8x dot dot dt. So here we'll be having 12t squared over 2 plus the constants, let me call it c1, because we are differentiating, we are integrating two times, right? So we'll be having two constants. So the first constant is c1. Then when we differentiate this guy once with respect to t, we have 8x dots. You understand? There is no constant. All right, so this guy is now 6t squared plus c1 equals 8x dot. But we want just x, so integrate again. Integrate 6t squared plus c1 equals to integral dt t equals integral 8x dot dt. So here we have this will become 3 t raised power, no. 2 plus 1, 3. 6 divided by 3 is 2. So you have 2 t raised power 3 plus t c1 plus c2 equals to 8x. Yeah, so from there, 2 t raised power 3 plus tc1. So I just want to make sure that I'm not wrong. So how do we get x out? So we just say x equals um, 2t raised power 3 divided by 8 plus tc1 divided by 8 plus c2 divided by 8. Okay, so 2, so we have x equals 1 over 4 t cubed plus 1 over 8 c1t plus 1 over 8 c2. Okay, so the next thing is no, we're given boundaries. I don't know, is it boundaries something? Okay, so x0 when t is 0, so this is what it means because this is like xt equals 1. So when time is 0, x gives you 1. When time is 2, when t is 2, x gives you 4. So we'll say x0 equals 1 over 4 0 cubed plus 1 over 8 c1 0 plus 1 over 8 c2 equals to, what do we have? 1, right? 1. So all of this becomes 0, all of this becomes 0. So we have 1 over 8 c2 equals 1. When we cross multiply, c2 equals 8. Good. Now the next one is x2. Okay, when x is 2, so you have x, and x is 2 equals, we come back here, so we have 1 over 4. This would be 2 raised by 3 plus 1 over 8 c1 bracket 2 plus 1 over 8 multiplied by 8 equals, no, c2 is 8 equals what's it? Where's the answer? Equals 4. So 2 times 2 times 2 raised by 3, 8. 8 divided by 4, you have 2 plus this is 1 over 4 c1 plus 1 equals to 4. So 1 over 4 c1 equals to 1 as 2 plus 1 3. It goes to the other side. 4 minus 3 is 1. So c1 equals to 4. So c1 is 4 and c2 is 8. Alright, so that's right. C1 is 4 and C2 is 8. Okay, so from there, all I just left with is to write the function, everything to write the function again. So the full function of x, where is it? Yeah, we got x here. So let me just put it here. The final solution that we are supposed to write. So we have x t equals to, can this place contain it? Let me see, what about here? So let's say we have x, no, x t equals to 2, where is it? 1 over 4, 1 over 4 t raised to power 3, right? Plus what's c1? C1 is 4, right? So 4 over 8, 4 over 8 t, right? Then okay, yeah. So you have 4 over 8 plus c2. C2 is 8. So plus 8 over 8. So that's your final function. So like we can just rewrite the whole thing again to be 1 over 4 t cubed plus 1 over 2 t plus 1. So 1 over 4 t cubed plus 1 over 2 t plus 1. So that's the solution. So we've been able to optimize this function subject to what x not equals 1, x2 equals 4. So that's the final solution. So you can see that it's not actually a difficult thing at all. That's all. So the next thing is for us to go into sufficiency conditions. Now, our sufficiency condition, let me just like prepare your mind. It's similar to what we did when we are doing border addition or when we're doing the Asian, you understand? So like when you have a matrix fx, fxx, fxy, fyx, fyy. So it's just the same thing. And even when we get to optimal control theory, it's the same thing. So like you've memorized one thing for three topics, which makes everything nice and makes studying kind of easier. So we'll get there. Yeah. So we'll jump right into it. All right. So we have these sufficiency conditions. I thought I even wrote that out. So everything we are doing, so everything is under sufficiency conditions. So all of this part is sufficiency conditions. So you want to know if your functional is at a minimum or like a global minimum, a local minimum, or what have you. So like I said earlier, so the conditions are kind of similar to what we did when we are treating the Asian. So given D matrix D as fxx, that's the second derivative of x, um, with respect to that's your df dx, so give you fx. Then you have fx, the x dots, which is the cross partial derivatives. Then you have the cross partial derivatives here too, but in a reordered format. And we have the direct second order derivative for x dot. So that's what we have on the board. So now, what are the conditions for a maximum? So I've divided them into two. For a maximum, if your determiner, if your D1, so your D1 is, this is a 2 by 2 matrix, so your D1 is the first value here. If your D1, which is equal to fxx, is lesser than 0, and if for concavity, your second derivative must be lesser than, it must be minus, to show that your curve is concave and you're talking about a minimum. So lesser than 0, and D2 is the determinant of the matrix, and D2 equals D, because we say it is equal to D because for you to find D as explained in the ancient video, D means determinant of this matrix. You understand? And that's the same as D2. You understand? So in the series of those classes, so we're talking about even a 3 by 3 matrix. So for a 3 by 3 matrix, your D1, your D will be your fxx, the first number here, the first answer that I have here, the first entry, okay, or the first elements of your um, matrix. Then your um, D2 will be equal to determinant, which is like looking at the first, you know, for how do I call it? When I explain it there, let me just talk about it briefly. So if you have a number here, number here, number here, number here, this. Alright, so your D, your first D, so let me call this A, B, C, D, E, F, G, H, I. So your D is just equal to A, whatever is here. Then your D2 is equal to, um, this is a D1 rather. So your D2 is equal to um, AE, so AE minus DB. Alright, so which is determinant, write it well, AE is determinant of these first four entries, 1, 2, 3, 4. So it's as if you are only limiting the matrix to um, a 2 by 2 format, like you are assuming this column and this row are not there. Now for you to be able to get your D3, okay, that's now going to be the determinant of the entire 3 by 3 matrix. All right, so that's not where we are going to. So when under calculus operation, for the ones that you'll be doing in this series, you only be limited to 2 by 2 matrix, so you don't have to like bother yourself with that. All right, So if d1 is equal to this and d2 is equal to that, d is negative definite and f, which is the functional, is strictly concave, making the extremal a global maximum. Now the difference between that and the next one is that if d1 because this is greater or equal to 0, so that's just the only difference. Yeah, if it's greater than 0, it's enough. And if it is greater than 0, it's enough. In fact, d has to be greater than 0 for everything. Alright, just like what we did in the Asian. So here, this is lesser than equal to that, this is greater than equal to 0. So once you have this kind of a thing, you no longer have a global maximum. What you'll be having is a local maximum. Right, and then, so what's, okay, before that, now for the minimum, so here you add strictly concave and negative definite. But here, once you have this kind of a result, so you'll be having all your, so look at the way this is structured. If the one is this, lesser than equal to 0, and this guy is equal to the determinant greater than equal to 0, when tested for all possible orderings. Alright, so here you now have anything like all possible orderings. So we are going to show that in an example. All possible orderings of the variables. D is negative semi-definite. So this one is just negative definite. This is negative semi-definite. And F is simply concave. It is not strictly concave. F is simply concave, which is sufficient for a local maximum. So the reverse is just what you have for minimum. If D1 is equal to Fxx, greater, here it was lesser than 0, here it's greater than 0, and here it is still greater than 0, right? I said D2 for everything has to be greater than 0. Alright, so here you'll be having um, positive definite. Positive definite because this answer here is greater than 0, it's going to be plus a positive number. Something greater than 0 has to be plus, 0.2 and 0.257, whatever. So it's positive definite, and F is strictly convex. So convex is what tells that your um, graph is at a minimum point. Okay, making the extremal a global minimum. Now for the other one, if d1 is because fx is greater or equal to 0, and this guy is greater than or equal to 0, so what are we going to be having? We got it right, simply convex, yeah, and there's going to be semi-definite. Okay, so the same when tested for all possible orderings of the variables, d is positive semi-definite, and f, which is the functional, is simply convex, which is sufficient for a local minimum. So what do we mean when we say global minimum, global whatever? Let's say you have a business cycle, you have something like this. Okay, so here is a minimum, here is a minimum, here minimum, here, business cycle, different years, you know, just showing a trend of your GDP, over different years. So here, let's say this guy is also minimum. So if you look at this, where is the minimum the deepest? So here. So this is a global minimum because it is the deepest over here. Alright. So others are local uh, minima. I don't know if that is correct. Local minima. So this is a local minimum, local. But the one that is the deepest, okay, is the global minimum. So here you have this is maximum, this is max, this is max, this is another maximum. So from the way I'm looking at this particular graph, I think this should be the global, it's kind of close. So I think this should be the global maximum here because it's the highest, okay, of all the maximum points. So that's a global maximum, the rest occupying the spaces of local, maximums or maxima, if that is right. So now how do we apply this to our question? How do we test for the sufficiency condition? So recall that I've rubbed it off, right? So, but this is what we had. So the functional. So the f, the x gave us 12t. This guy. Now the f, the x with the dot, it was 8x dot, which is same as our fx dot, right? So now what we are looking for is the second order direct partial derivatives and the second order direct um, derivatives and second order partial um, derivative. So here we want fxx. So the x is fx, right? So fxx, that is we are differentiating 12t with respect to x. Or there's no x there. So this one becomes 0. Alright. Fx is also 12t. So fxx dot, that is the cross partial derivative. So there's no x dots as well in this place. So when you differentiate fx with respect to x dots, you also have 0. All right, and then we know that fx x dot is same as fx dot x. This one is also equal to 0, right? So then the last one, fx dot x dot equals to, so here fx dot was this 8x, like the f the x, the first derivative. So it's this. So the second derivative now will be differentiated with respect to x dot again. This was our result for the first. So for the second is going to be 8, right? So our d, so we have 0, 0, 0, 8. So if you look at this, our fxx equals 0, right? So then that's which is the value of our d1. So d1 is 0. Then d2 is equal to the determinant, which is then equal to, what is the determinant? 0 times 8, 0. 0 minus 0, so you have 0. So if you look at this, it does not, this is this does not fulfill, what do you call it? So this does not fulfill any of these conditions. So this condition says if fns is lesser than 0, or there is not lesser. Yeah, if it is lesser equal to 0, but we are not so sure. So what we are going to do is, when we have something like this, this is what you will likely have, what we have in B here, or what we have in the B of this part, because for this fss has to be greater than 0, it's not greater than 0, and for this fss has to be lesser than 0, or we can say that our fss is not lesser than 0. So that is where, for all possible orderings, comes to play. So what will be happening here is we will reorder this matrix. So here, this was the first stuff, first entry, first element, second element, third element, and this is the fourth element, the last one. So when we reorder it, so the fourth becomes first. So you have d equals to, so you have fourth, third, second, first. So we reorder it. So in this particular case now, so our our d1 equals fxx equals to the first entry here, 8, right? Then our d2 equals d is 8 times 0, 0, 0 minus 0, 0. So this fulfills which condition now? If you look at it, so we are having, for both, we are having our d, this is positive, so we are having our d1 greater or equal to 0, right? Then we just take it like, I don't know why it is written like that, but the other one, d2 equals the determinant is 0 there, but we write it as greater or equal to 0. So that's how we're going to write. What really determines it is your your d1, right? So where do we find that? Where d1 is greater? So here, yeah. So which means that our our function. So how do we write that? Write since, okay, let me write the conclusion. So since d1 since d1 is greater or equal to 0 from what we have, and d2 equals d greater or equal to 0, so d is of course positive semi-definite, positive semi-definite, definite, and f is simply convex, right? Showing, revealing or showing, okay, which is significant for, not significant rather, which is sufficient for a local minimum. So that's that. We are done solving the question. and testing for the sufficiency condition. So if you have any question, leave them in the comment section. I have a question for you anyways. So so you have an assignment, so I'll write it there now. The assignment states that you should maximize that function and as 3x dot squared plus 36xt plus 13t with respect to time, okay, the t subject to say x not when time is 0 equals 2, then x one equals 4. And when you are done, you comment on the sufficiency conditions. Of course, it shouldn't take you much time if you've properly understood what I've explained here. You don't have to be right out of these things anyway. So just use the one that's applicable to the question that has been given as your assignment, and of course you know how to submit your assignment. So I will be having a second class on the calculus of variation. So after that, we move into optimal control theorem, at least for now. So thank you very much for watching this video. See you in the next one.